This is an example of a problem where you're going to need to find equilibrium concentrations of some species of a reaction. So first I'll read the question. If a reaction mixture initially contains 0.175 molar SO2Cl2 with nothing else, find all equilibrium concentrations given this equilibrium constant of 3.00 times 10 to the negative 7. So the first thing that we want to do when we see these is check to make sure that the equation is balanced. So in this situation, the equation does not need any coefficients. It's already balanced as is, which makes our lives a little bit easier. So we're going to solve this problem using an ICE table. So first we need to talk about the initial concentrations of the species that we're starting with. So in the question we know that SO2Cl2 starts with 0.175 molar. And there's nothing else in our reaction vessel, so these are going to be 0. Now we need to determine the change that happens as this system shifts to equilibrium. So this molarity is going to change by negative x because this is getting used up as it creates these two products. And since this starts at a certain concentration and these start at no concentration, we know that our reaction is going to move to the right. And these are going to change by positive x, because the concentrations of these must go up. Now, at equilibrium, we know that this concentration is going to simply change by x. And the reason why these are just x's by themselves and they have no coefficient in front of them is because in this equation, it's already balanced without coefficients. So since there are no coefficients here, there are no coefficients on our x. So now we say that at equilibrium, SO2Cl2 is going to be 0.175 molar minus x, and these are just going to be x because they started at 0. 0 plus x is just x. So from here, there's two things that we can do to solve. The first thing that we have to do to get to either of those ways is to set up an expression for K sub c. So I'm going to write that over here. The K sub c expression is equal to the concentration of SO2 times the concentration of Cl2 over the concentration of SO2, Cl2. And we know that these are all raised to the first power because once again there's no coefficients on this equation, which means they're all just raised to the 1. So now what we can do is plug in our concentrations at equilibrium into this equation that we have right here. So that's going to be x, because that's the constant, that's what SO2 is. Also x again, because that's what Cl2 is, over concentration of SO2Cl2, which is going to be 0.175 minus x. Okay, so if you simplify this, you're going to get x squared over 0.175 minus x. Okay, so now there's two things that we can do to solve for x here. One way is the x equals small approximation, and the other way is a quadratic equation. So I'm going to show you both. I'm going to start with x equals small because it's easier and it's faster. So if we take a look at our equilibrium constant here, we see that it's 3.0 times 10 to the negative 7. Now that's a very small number, and if we have a small equilibrium constant, that tells us that at equilibrium, this reaction greatly favors reactants. So it lies a lot to the left side. And since this number is so big, it means it's very significant. There's going to be very little product and a lot of reactant. So since that's the case, we know that if we change this molarity by just a little bit, if we subtract some off or bring some back on, it's not going to change it that much based on sig figs because it's so different in comparison to these two concentrations. So we can try to use our x equals small here, and by doing that, we're just going to say if we have any number minus x or plus x, we're going to ignore the x and pretend like it's not there because we're assuming that it's very, very small and it's not going to impact the molarity that we're given hardly at all. So using x equals small, I'll write that off to the side so we can keep track. We would say that this expression is then equal to x squared over 0.175, okay? And we're given a K sub c, so I'm just going to go ahead and plug that in right here, times 10 to the negative 7. And then it's very easy to solve from x. All you have to do is multiply each side by 0.175 and then take the square root. So in using x equals small, we get that x equals 2.29 times 10 to the negative 4. Okay, so that's a pretty small number, and that's a good indication that our x equals small probably worked, but that's not good enough because if you use x equals small, you have to have some way to justify it. So the way that we do that is we take the number that we got for x, 2.29, times 10 to the negative 4, and we're going to divide that by the molarity that we were given at the beginning, 0.175. And we're going to multiply that by 100 to give us a percentage. So what this is doing is it's basically just setting up a ratio of what x is to what we know is happening in this reaction. And if it's a small percentage, less than 5, then we can say yes, the amount that the molarity is changing based on what we're taking away, which is x, is really insignificant. So if you do this, you end up getting 0.1309%, which is definitely less than 5, and we know that our x equals small worked. Okay, so that gives us a value for x, which makes it pretty easy to determine equilibrium concentrations. But I want to show you how you would do it with the quadratic equation so that you will know that x equals small is actually pretty good. So if we go to quadratic over here, we start essentially with the same expression, but we have to get the x's by themselves. And once you do that, you're going to end up getting 3.00 times 10 to the negative 7 times 0.175 molar minus x equals x squared. Okay, so that's just a simplification of this step up here. If you multiply this over, and you end up with x squared on the side there. And then once you simplify and get x on the same side and distribute here, you're going to get 5.25 times 10 to the negative 8 minus 3.00 times 10 to the negative 7 x minus x squared equals 0. And now I'm going to rewrite this so that we have a positive x squared just to make our quadratic a little bit easier. And then that's going to end up being plus 3.00 times 10 to the negative 7x. And then minus 5.25 times 10 to the negative 8. That still equals 0. So when you do our quadratic equation, we know that that is A, this is B, and this is C, the coefficients before the x's. And then if we plug that all into our quadratic equation, we get x equals opposite B plus or minus the square root of B squared minus 4AC AC all over 2A. Okay? So then the next step here would be to multiply this out and say this number minus what you get there. And that is going to give you this part, and the denominator remain unchanged, plus or minus the square root. When you simplify these terms and add them together, you get 2.1 times 10 to the negative 7. And then you're still dividing by 2. So now all you have to do is take the square root of this number, and that is going to give you x equals negative 3.00 times 10 to the negative 7 plus or minus 4.58 times 10 to the negative 4. And it's still going to be over 2. So now from here, there's two paths that you can take. You have to do this number plus 4.58 times 10 to the negative 4, and this number minus 4.58 times 10 to the negative 4. So I'm going to do those both down here. Negative 3.00 times 10 to the negative 7 plus 4.58 times 10 to the negative 4 over 2. And then x equals negative 3.00 times 10 to the negative 7 minus 4.58 times 10 to the negative 4 divided by 2. And in this instance, x is going to give you 2.2 2.289 times 10 to the negative 4. And on this side, x gives you negative 2.289 times 10 to the negative 4. Okay, so you can see that this x that we got from doing quadratic is the same by sig figs as the x that we got from doing x equals small. And that's good. That means that x is really small and it's basically negligible. But in using quadratic and x equals small, we've basically double checked that we're right. So I'm going to erase all of this quadratic working so that we can finish up the problem. So now, just because we have x doesn't mean we're necessarily done. In this instance, x is going to give us the equilibrium concentrations of both of these product species, but we also need to figure out what the equilibrium concentration of SO2Cl2 is. So to do that, we can say concentration of SO2Cl2 is equal to 0.175 minus x. And if we plug in our x, that's 0.175 minus 2.29 times 10 to the negative 4. Okay? And 2.29 times 10 to the negative 4, when it's subtracted from 0.175, that's going to give us an equilibrium concentration of 0.1747, which by sig figs is equal to 0.175, which is what we started with. Another confirmation that x equals small was a good thing to do. And then we say our concentration of SO2 is going to be equal to just x, and that is 2.29 times 10 to the negative 4 molar. And that's a molarity as well. And then Cl2 is the same situation as SO2, 2.29 times 10 to the negative 4 molar. Okay, so that does answer our question, but you might be thinking that this seems like a really small molarity, and in fact it is, but it's a good thing that it's a small molarity because if we look back again at our case of C, we see that it's very, very small, and that means at equilibrium, our reaction favors the reactants. So our reactant concentration here is much higher than either of our product concentrations, and that does work with the information that we're given in the problem.